Hi, I'm Kefan, an assistant professor in the physics department at UW-Madison. In this video, my colleagues and I will tell you about the research activities at the Wisconsin IceCube Particle Astrophysics Center, the WIPAC.
Currently, we have 6 faculty members at WIPAC. We are working on a range of astroparticle experiments, including neutrino experiments, the IceCube Observatory, and the Askion Radio Array, and the gamma ray detectors, the Cherenkov Telescope Array, the High Altitude Water Cherenkov Gamma Ray Observatory, and the Fermi Gamma Ray Space Telescope. Human eyes are sensitive to visible lights from red to purple, but the universe shines in energies that are billions to millions of billions times higher, and that's why we build astroparticle detectors to see the invisible universe. Between 10 to the 12 to 10 to the 15 electron volts, we have observed high-energy neutrinos from extragalactic distances, and we are building the next generation detectors to see neutrino up to 10 to the 18 and even higher energies. Between 10 to the 8 to 10 to the 14 electron volts, our detectors, including the CTA and the HAWC, have captured many sources that emit gamma rays. When an astrophysical event occurs, such as a binary neutron-star merger, different types of messengers are produced. By collecting neutrinos and gamma rays, we get a full picture of what the astrophysical sources looks like. WIPAC is an active participant and a leader of this so-called multi-messenger astrophysics. Specifically, WIPAC is the home of the IceCube Neutrino Observatory. IceCube is a cubic kilometer particle detector located at the South Pole. It is buried in the ice, extending to a depth of about 2,500 meters, and that's about 8 times the height of the Eiffel Tower. When a neutrino interacts with the ice, it produces electrically charged secondary particles that emit Cherenkov light. The IceCube sensors collect this light, digitize it, and eventually send it to our operational center at UW-Madison. We then use the footprints of the neutrinos and muons to reveal their direction and energy. In 2013, IceCube made a breakthrough discovery of neutrinos of astrophysical origin. And since then, IceCube has opened up a new window to observe the universe. Today, IceCube is contributing to researches in many different frontiers, and in particular, the IceCube groups at WIPAC are actively working on point source searches, measurement of diffuse flux of cosmic neutrinos, neutrino oscillations, flavors, searches of transient sources, and many other projects. We are developing the next generation IceCube detector, IceCube Gen 2. IceCube Gen 2 will be 10 times larger than IceCube in volume. It will also contain a radio component that enables the detection of ultra-high energy neutrinos. As a step toward the IceCube Gen 2, WIPAC members are working on the IceCube upgrade. This funded project will deploy 750 advanced photodetectors and calibration devices inside the existing IceCube detector, which will significantly improve the detector's sensitivity at lower energies.
The IceCube upgrade is an extension of additional optical sensors to the current IceCube operating IceCube Neutrino Observatory. It will be on the order of 800 new advanced photodetectors deployed deep within the existing IceCube detector and connected pretty much in the same way using cables and integrated into the IceCube data acquisition system.
In addition to the IceCube project, in which all faculty members are involved, the WIPAC groups are working on the following experiments. Albert Carlos' group is developing the Askion Radio Array. ERA is a radio detector array currently under deployment at the South Pole, designed for the detection of ultra-high energy cosmic neutrinos using the emission of radio waves produced by their interaction with ice. Justin Vandenbroek's group is leading the hardware development of the Cherenkov telescope array. CTA will use dozens of imaging atmospheric Cherenkov telescopes to detect gamma rays between 30 GeV and 100 TeV. A prototype telescope has been completed, and earlier last year, the first gamma ray air shower was identified by this protodetector.
What we're doing with the Cherenkov telescope array is viewing light that's 1 trillion times more energetic than we can see with our eyes. These trillion electron volt gamma rays, each one of them collides with the atmosphere, and it basically shatters a molecule of air. Now, some of those particles can emit a flash of blue light called Cherenkov radiation. And so what our camera does is that it collects that flash of Cherenkov light, and together you make this movie at 1 billion frames per second of the air shower, the air cascade of particles developing in the atmosphere.
And finally, my group is working on the HAWK observatory. HAWK is located near Puebla, Mexico, at an altitude of 4,100 meters. It is composed of 300 water tanks. The sensors at the bottom of the tanks record the footprint of a particle that interacts with the water, which is later used to reconstruct the arrival direction and energy of the particle. HAWK observes the universe at the highest photon energies. It has revealed many new faces of our universe that are unseen at lower energies. For example, our group used HAWK to picture a set of jets from a mini black hole in our own galaxy. We also find an extended gamma ray cocoon that was inflated by stellar activities. And HAWK can also be used for indirect dark matter searches. For example, it found an unexpected gamma ray halo surrounding the Geminga pulsar and suggested that dark matter might be needed to explain an excess in the cosmic electron spectrum. In summary, YPAC is actively involved in astroparticle studies over 13 orders of magnitude. Like what our previous student said, you will find life here full of excitement. Well, still sometimes some problems to solve.
Connection, we're breaking, right?
What do you mean we're breaking? We're
I mean,
not
like
breaking
it's
anything.
crimped right now, but like this side of this cable, the vault
Yeah.
side is we're removing, right?
Yeah.
So I can do this.
Well, that's a good problem to solve. Welcome to join us at YPAC.